It's a pleasure of mine to introduce Andy Mueller. He's one of the maintainers and release managers of scikit-learn, the premier machine learning package in Python. Also, Andy works for Amazon, so he's been there for, I think, a year now. And Andy's going to be talking to us about commodity machine learning.
Thanks for that introduction, and thanks everybody for coming so early in the morning. I heard it was a long night. So I want to talk about commodity machine learning, and what I mean by this is that I think machine learning should be easy and should be for everybody to use. And I think we're nearly there. So in particular, I want you to use machine learning. I think whatever your application is, whatever your business is, basically everybody can profit from using machine learning. And we're really at a stage where you can simply do this even without a lot of expert knowledge. So I know probably most of you are familiar with like basic machine learning concepts, but I still want to repeat a little bit on what machine learning can do for you. So the most basic and most classical machine learning task is classification, where you have some data points and you want to assign a class. For example, in spam detection, you're given some emails and you want to say, are they spam or are they ham? So this is a binary classification task. You're getting a data point, you want to say spam or ham. There's two classes. Another classification task that's used quite a lot is click-through prediction, or CTR, where people are shown ads, like here on Facebook, and you want to predict will the user click on this ad or not. This is a bit more tricky than standard classification because you're usually interested in how likely is it that a user will click, because actually clicking happens only in 0.01% of the time or something, so you cannot actually predict when it happens, but you can estimate a probability for that. So the second really big field of machine learning that's used a lot in practice is recommendations. So for example, here you can see that Amazon was one of the first to actually do this a lot. So there's several recommendation systems going on. Here in the bottom you can see customers who bought this also bought that. Recommendations drive a lot of what you see in social sites, what you see on Facebook, on Twitter, and if you listen to Last.fm or Spotify, all of these use recommendations. And maybe as a last application here, there's ranking, which means given a search query, give the most relevant results. For example, if you do web search or something like that, or even just searching within a page, usually the way it is done is you use something like Elasticsearch to get tens of thousands of candidate hits, so retrieve these documents and then do a machine learning approach on top of that to re-rank and say get a top 10. They're really relevant for the query. And so as I said, applying machine learning is already quite easy. So I think with the tools out there, particularly with scikit-learn, it's really easy and a lot of people can use it. But I feel like it should still be easier to use. And I want to talk about what I think is still missing and what we already achieved. So I guess you're all familiar with the scientific Python stack, which is my favorite tool for doing machine learning, and hopefully yours too. And particularly I want to highlight three libraries or three projects that drove adoption of machine learning. The first one is the IPython notebook, which makes data exploration much more easy and much more interactive. It also takes away a lot of the fear of programming that some analytics people might have, because you don't need to open an IDE or anything like that. You can just work in your browser and you get results directly and you can visualize. The second one is Pandas, which gives you all the tools and functionality you need to analyze your data, to visualize your data, to work with like unclean data sets in particular, to work with dates, and to do all the crunching that you need to do before you can actually start with machine learning. And last but not least, obviously, scikit-learn. And I want to talk a bit more about why I think scikit-learn has been successful. So I mean, so first I want to say, well, it is indeed successful. So here are some of the companies that admit to using it, and I'm pretty sure there's a lot more companies that actually do use it. So I heard a couple of talks where there are other companies using it that are here. So if you're using scikit-learn and you're not on the testimonial side, send us a testimonial, because it really helps us get sponsors and get grants at university, which helps us improve the software. And apart from the use in industry, there's also 500 or 600 research papers that use scikit-learn, and that again, that are the ones that actually say they're using us probably twice as much. And so one of the reasons I think scikit-learn was so successful, or is so successful, is that it's pretty simple and has a very straightforward interface. So to solve a classification task, basically this is what you have to do. It's 4 lines of Python code. I think everybody can do that. So you get your model from scikit-learn, you instantiate your model, you call fit to actually learn the model. So machine learning actually does 1 line. So I don't think it can get much easier than that. And then predict to apply your model. Obviously, this is not the whole story. There are things like setting the parameters for the model, doing model selection, doing pre-processing for the data. But the core of machine learning is really these couple of lines. And I think this is one of the one of the reasons for scikit-learn's success. And so I mentioned spam filtering before. So actually, to build a fully functional spam classifier, this is what you have to do: 3 lines of imports and 3 lines of actual code. So for Mueller, the standard classifier, or the classical classifier for spam classification, is naive Bayes, and so we import that. The second line imports the count vectorizer, which I described in my tutorial like 2 days ago. What it does is basically it transforms the text data of the email to a matrix representation so that the machine learning algorithms can work with it. And so make pipeline just puts these two together. So first you pre-process your text data, make it into a matrix using count vectorizer, and on top of that you learn a naive Bayes classifier. And this gives you a fully functional spam classifier, given you have some labeled data. The second reason why I think scikit-learn was successful was because there's really a wide array of algorithms. I don't want to go through these, but a lot of people said just, if you pick any machine learning model, the chance that's in scikit-learn is pretty high. So actually we try to have all models that are in elements of statistical learning, one of the major books in machine learning, and also that are in pattern recognition and machine learning by Bishop. And I think we're nearly there. There's maybe 2 models missing from the classical ones. And I think the third and also very important factor for the success of scikit-learn was this. So we did a poll, I think like a year ago, on what people think about scikit-learn and what they think is bad and what is good. And this was a kind of typical answer, or maybe a bit of a hyperbole. So someone said, the scikit-learn tutorial documentation is so good one doesn't need a textbook anymore to learn a new machine learning method. So as I said, it might be a bit of a hyperbole, so I totally encourage you to read as much machine learning textbooks as you can, but still, I think it's quite telling that people use the documentation this way. And I've seen documentation be referenced outside of scikit-learn context, or just in general machine learning discussions. Someone asks, how do you do X? How do you do Y? How does this algorithm work? And people reference the scikit-learn documentation and not Wikipedia. So I think we can feel pretty good about that. So I think that it was enough patting ourselves on the back. So yeah, but this is not enough. So we have good documentation, we have a good library that people can use, but there's still areas where machine learning in Python or machine learning in general is lacking, I feel. And the way I think about this is along these 2 axes that are shown here. One is the amount of data that we can actually process, so the data set size. And the other one is the amount of automation that we have, or on the other hand, the amount of expertise that is needed. So Ideally, I want to be everybody to use machine learning, no matter what their background is. And so I want to label these axes just a little bit. So for dataset size, I think there's 3 main categories that are interesting. So small data is the one that fits into RAM for me. Then there's like a middle ground where you can process data on a single machine, but it doesn't fit into RAM anymore. This is often called out-of-kernel learning. And then there's infinite scalability, which is what I call basically Hadoop or Spark, or you have something on the cluster in HDFS, and you can always buy more machines. And then in the axis of automation, well, on the one hand, you have libraries, which are like scikit-learn or pandas, which you can use to make predictions, but you have to roll your own program every time. So you have a large array of functionality, but you definitely need to code to make anything out of it. And on the other end of the spectrum would be a one-click solution, which says just like, here's my data, do machine learning. And and this is how I actually see what's out there at the moment. So the Python ecosystem is mostly in this lower left corner, where, for example, pandas and scikit-learn both really, they need you to code. Pandas really provides kind of very convenient but sort of low-level functionality. Scikit-learn abstracts away a bit more from the user, but they both basically work on a single machine. There are some tools that work on more data, but not really for machine learning in Python. And so these really mostly work on the RAM. There's very little automation. There's a project called Skull or Scikit-learn Library, which makes it easier to run experiments, but this is still quite manual, and it doesn't necessarily need you to write programs, but it's not very flexible yet. And then there's like this whole other side, which is basically cloud computing or machine learning on the cloud. And so we have Blaze there at the bottom, which is really sort of the only thing that is really in the Python space completely, which is a new project by Continuum. It's still, I would say, in the early phases, and actually, yeah, I think it's a great direction, but it's definitely work in progress. And also, it's more like on the level of pandas. So the idea there is to have a distributed data frame, basically. So it doesn't give you any machine learning tools. It just gives you okay, it's a very hard task, so it just gives you distributed representation of your data. Then there's, so one of the most promising projects at the moment, I think, is Spark together with MLlib. So Spark is a distributed in-memory framework for parallel data processing. So this is actually what Blaze is now built on. And MLlib is a machine learning library. So in a way, this is the same level of abstraction that you have in scikit-learn. You have a library that gives you machine learning functions. You can apply these functions to do your machine learning. It has the great advantage that it can work in arbitrary data sets. So I think this is will be a very, very useful tool in the future. However, it's not really there yet. And also, it's Scala, which is maybe not that nice for us. I don't know. So I think we should think about how can we put Python more in this space. So even if we would have Blaze, we still would not be where MLlib is at the moment. And then going to more automation, there's these more or less commercial products. So there's Azure ML, which was recently announced by Microsoft as a cloud machine learning solution. So this gets away all of the sort of hassle of installing your own cloud, but in the end, it still also just provides the library, so you have to roll your own solution still. Then there's Databricks. So they released a very cool solution quite recently. You should look at their Spark Summit keynote if you haven't done so. They actually have a solution that includes both a Python front end and a Scala front end, and does cloud computing and very amazing visualizations. The main downside there, so this is all built on Spark and MLlib. The main downside there is that as a company, it's completely closed source, so basically we cannot use it, and even their beta is closed. And maybe there's way more startups in this space, but I just picked out like these two and Azure ML because I think they're kind of interesting from their from how they approach the problem. And then there's Prediction.io, which I maybe should have put more on top. They are actually an open source company, so they built an open source product that detects more of the verticals. So they don't give you a library to build your machine learning solutions. They give you a framework where you can do things like recommendation or ranking or classification. So this is much closer to the one-click solution. They give you something that you can directly integrate into a web application. Yeah, but still, but actually they don't have any Python support at the moment, I think. And Azure ML will probably have Python support hopefully quite soon, but at the moment there's nothing there. So yeah, so you can see we're very good at the lower left. There's something happening in the lower right, but the rest is pretty empty. So now you could say, well, you argued that we should actually be like, we should have something very automatic that is infinitely scalable, so you want to be at the top right. And so we're in the top bottom left, so maybe we should just throw out all of scikit-learn and pandas and not use it anymore and work on something like do Scala. But obviously that's not what I want to say. So I would argue that it's important to have sort of something in all four corners of this diagram, to have some tools in, for each of these applications. And that's what I want to talk about next. So first, I think a lot of people approach me saying, hey, can you do scikit-learn on Hadoop or Spark or something like that? And usually my answer is, so why would you want to do that? Because in 99% of the cases, a single machine is enough. And yeah, probably some people don't believe this, but I want to explain to you why. So the first reason why I think a single machine is enough is because this is sort of the single machine I usually use, and it's the single machine that you should use if you have a bit more data. So that's like standard EC2, 32 cores, 256 GB of RAM. This is way cheaper than hiring 3 data scientists to set up your Hadoop cluster. Don't set up a Hadoop cluster if your data fits on this machine. You can just get this on EC2, or I don't care, you can get this also from Azure or something like that. And you can just run scikit-learn or even R or whatever you want on this. And it will be super fast, super responsive, super easy to install. And really, do you really have that much data? I don't know that many companies that have more than 250 GB of interesting data. And the other reason why I think this is the case, or why I think people don't have that much data is, so I'm talking about machine learning. I'm not actually talking about big data. There's a big difference for me. So big data is usually very unstructured data like logs or Twitter posts. But as I showed in the beginning, usually if you're doing machine learning, you're mostly doing supervised learning. And in supervised learning, you have your data, and also you have a label that you want to predict, like for an email, is it spam or not spam, or will a user click the ad or not click the ad? And this is very, very structured data. And in the huge amount of logs that you maybe gathered about your users, most of the data will not have this kind of structure. But this is really what is very valuable, having these labeled samples, because they allow you to predict something for the future. If you're lucky, you can maybe have this from the past. So for these click-through example, you can gather from the past whether someone clicked on something or not. And or if you want to do stock prediction, you know how the stock behaved in the past, and you can try to learn how this will be in the future. But if you do spam detection, you have no idea whether an email was spam or not, unless a human said this is spam or this is not spam. If you do fraud detection, if you do sentiment analysis for a tweet, you can't really find out after a tweet was sent whether it was happy or sad or angry or neutral. A human has to go in and label it as such, so for the data to be really useful and valuable. And so after you do that, I really doubt that you still have like 2 billion data points. So this is why I think that for most people, just get a big single box and you'll be very happy, and much happier than setting up some Hadoop cluster. So this is the reason why I think being on the lower half of the, being on the left half of my plot is a good idea for most people. And I also think being sort of on the lower half of the plot, so doing something that is not as automatic, is a good idea. Because we do need open box methods where you can go in and do analysis by hand. So this is actually probably what most people do here, is they dig through the data, they use pandas, they look what are the important features, how do I have to clean this up. And for this you really need these open box methods. You need to try out different classifiers, different pre-processing. And so to really get the most of your data, you have to do this. So there's probably no way around it. So I think probably people will agree that it's important to have open box methods that allow you to really get deep insights into your data. On the other hand, I think we also need black box methods, and this is something that we haven't really done so far. So one of the reasons why I think we need black box methods is that, I don't know if you saw this, this is kind of a gag chart that I made a while ago on how I think you should do machine learning. No, actually on how I think I should do machine learning. It tells you sort of if you use scikit-learn and you want to do regression, classification, or clustering, sort of what kind of methods I would use. And the sad thing is that actually I do that. So if someone gives me a data set and I go through like, is this text, is this not text? How many data points do I have? Will I use a linear classifier or non-linear one? Can I do nearest neighbors? And so if I can write down this chart, then I can make this automatic, right? So often I spend like, I don't know, a day, 2 days, or a week just trying out all of scikit-learn on a classification problem or on a regression problem. And I feel like I shouldn't be doing this. I actually have better things to do. And so if I can write down this chart, I think we can automate this. And I think a lot more effort should go into this. And so basically, the program should automatically try whatever I would try first. And then after that, I open the box and look in what are the important features, what does the data mean. But before that, I would just throw the kitchen sink at it and just like do scikit-learn for me. And so that's how I want it to look. So basically, when someone gets me a new data set, I put in my data and I say, predict, and then it'll give me a dashboard and say like, hey, I tried all these scikit-learn models and I tried all these models and these are the important features. This is what worked, this is what didn't work. And then once I have that, then I can go in and dig deeper. But really, the machine shouldn't need me to do that. And currently I have to do all of this manually, which I think is kind of a bit of a waste of my time. And the good news is there's actually tools out there to do this already, at least to some degree. This is called automatic machine learning or hyperparameter optimization. This was particularly popular in the deep learning community because neural nets are hard to train and have like billions of parameters now. Okay, they have billions of parameters, but tens of hyperparameters. So it's very hard to tune them by hand. And there's, for example, these 3 projects that came out of it, or these are more research projects to select architectures for deep learning models, but they can be more widely applied to select machine learning models. And so, because I think they're cool, and because someone asked me about it, I put in this slide to explain how they work. So they use this framework of Bayesian optimization. So I stole this slide from some tutorial of Nando de Freitas. I mean, obviously this is what's called global optimization. So you have a pretty unstructured search space, and you want to find the optimum. This is an NP-hard problem, so all bets are off. But this works well in practice. So the idea here is, imagine you only have one parameter that you want to adjust, like the regularization or something like that. And that's depicted on the x-axis. See a pointer? Probably not, right? Okay, so let's say you try 2 points that you saw, like 2 settings of the parameter at the top. So you have these 2 black dots labeled with observation. And this is sort of, you tried this parameter and you got this result. You tried this other parameter and you got this result. What you do now is you fit some probabilistic model, regression model to this, for example, a Gaussian process. So this Gaussian process will give you the solid black line here, which as the mean, and this purple kind of cloud thing as the variance. So the Gaussian process will think, well, this is where this function is, whereas the dashed line is the true function. And you want to find the optimum of this true function, so the maximum, which is sort of somewhere on the right. And so now you want to say, what's the next model that I should try? So what's the next parameter of the, what's the next parameter of the model that I should try? And the way these work is they compute this acquisition function that you see in green on the bottom. And wherever the maximum of this acquisition function is, this is where you'll try where you'll try the parameter next. So the idea is that to evaluate this dashed line means training a model. This is super expensive. You have to, if you're unlucky, you have to start up your Hadoop cluster and run some big MapReduce job. Or you have to train scikit-learn. It's not that slow. And but evaluating this green function is very simple because this is just computed from the Gaussian process that you fitted. And the idea is this, this green function combines both where you think the function is very high and also very, very uncertain. So at the right node, the function is very high, but you're also very certain. So that you won't try this point again. But around it, so this is the highest point you have. And around it, the uncertainty spreads. And it's probably also going to be high around this high point. So this is why the green curve is pretty high around this point that you tried, and it was good. So it'll find the maximum of the green curve and try out this parameter next. Then you get a new observation. And then you refit your Gaussian process. You get a new uncertainty and a new mean function. You can recompute your acquisition function. You get the maximum of that one. And you have a new point to try out. And then at some point, if you do this long enough, you'll have somewhere where the maximum of the acquisition function is at a place where you're very certain what the function is, and then you're done. So this is a very neat way to do this global optimization, to search over models, and to work with a function that's very expensive to compute, like training a whole model. And we should really do more of this, I think. Yeah, so anyhow, let's go back to my diagram. And so I said that I think most of the time we really don't need more than one machine. So actually, even at Amazon, I had no application that didn't fit on this one box. And, okay, maybe I had one, but basically all of them fit on the one box. But still, I mean, sometimes you need to scale beyond a single machine. So, for example, we have the thing like the Kindle that you probably know, and we have books on it. And sometimes we try to do learn a language model, for example. And so what do we take as a corpora? We take all the books that are on the Kindle. So that don't fit on a single machine. And in particular, if you want to run a model on this, like this is a lot of data, and so you actually want to distribute this. So there are cases where you want to distribute. Or if you're Twitter and you want to do analysis all the tweets that come in at once and do spam detection on them, probably you also need more than one machine. But I think this is really the rare case. So yeah, so let's get back to my diagram. So I think, as I said, in the lower left corner, we're pretty good off. And on the right hand, so this is what I think about it. So I think we're pretty good off in the left-hand corner. I don't want to say like this is done and we don't need any more work there, but I think we're in a pretty good situation. On the right-hand side, we have some interesting ideas, some good developments. Unfortunately, I feel like Python is not as far as Scala there, and also the open source solutions are really lacking behind the commercial solutions. And yeah, I really put my hopes on Blaze and somewhat on MLlib, and let's see where it goes. But actually, I think we should focus more on the top of the chart. So having something scalable is great, but for most of us, it's not as important. It's more important to have something working quickly and with less work, so that we can spend on our time to actually design better models and do more meaningful work instead of trying out. So I don't know about you, but I try out too much. And I think we need to automate this more. And this is why I think we should really focus on the top of the chart where we're not really happy yet. Okay, I think I'm a bit too fast, but that was all I had for today. Thanks.
Okay. Thank you very much for that awesome keynote. So now let's take some questions from the audience. So, yeah, there's a question.
I was wondering, so you said that what pushed the quantum machine learning further off the chart is. Can you hear me?
Not really.
Hi. So you said you want to push machine learning more to the top of the chart, to the one-click solution space.
Yeah.
I was wondering that quite a lot of the work actually goes into cleaning the data and selecting what you feed into the machine learning method. And then once you've done that, you can then try out 1,000 different solutions and see what comes out. But how do you think cleaning the data, is that something that could be automated?
At least partially, I think so, yeah. I think cleaning the data is also very important, and then this is definitely a step where there's a lot of manual work going into it. So I think you can kind of automate it, but I think it will be easier to just try to work with the unclean data and see what comes out, or like clean it up roughly automatically and see what comes out. Then afterwards, you can see what worked and what didn't work. So that would be my approach at the moment. It's a very hard problem to do this, and actually, so I'm more comfortable in automating machine learning and automating data cleanup, maybe because I feel this is easier.
Any more questions?
Yes, I think I have a similar question. So I always felt that the features that you actually put into the machine learning method are much more important than the classifier, for example. So in computer vision, this is often the case. I mean, do you think that could also be automatically handled? Or
yeah.
Is there anything in scikit-learn for that?
So there's nothing in scikit-learn for that yet. There's, I think, much too few automation scikit-learn. There's ways to automatically generate features. I wouldn't say so much for computer vision. In computer vision, I think really at the moment we're at a point where we should try more deep learning and conv nets, because that really worked quite well at the moment. Yeah, it's probably not the final answer, but I don't think we can automatically generate like new computer vision features so easily. I mean, you could try out a battery, say like do sift, freak, whatever, LBP, and try to select these. So if you know you have these, then you could do automatic feature selection. Actually, yeah, some people use these Bayesian optimization. A friend of mine uses to do feature selection, but you would have to specify sort of at the beginning what kind of things you want to search over, right? Does that answer your question?
Yeah, sort of. Right. Yes.
So, and also a question linked to that. So, I really enjoyed your talk about commodity machine learning. Do you believe that machine learning is becoming a commodity, and then linked to those questions that data science is going to become data processing science instead of actual machine learning? Because if it's a commodity, then it's just like preparing the data and then press play on your ML service, and that's it. Very excited about this. Do you believe machine learning is becoming a commodity?
I hope so, at least partially. So a lot of the problems that have actually interesting structure, and you will not be able to capture the structure of the problem using something very automated. But from my experience in industry and what when I talk to people, a lot of people use binary classification because it gives them a good enough solution for the problem. And so I don't want to spend my time designing binary classifiers. And I think this will definitely become a commodity.
I'd actually like to ask a question. So sort of perhaps one of the hurdles in turning machine learning into sort of something that is commodity is actually sort of deeply understanding the methods. So like deeply understanding sort of the mathematics behind each one of the methods, and not just sort of blindly sort of applying them and seeing which one works best. Do you think there's a way to tackle this?
So, kind of. I mean, in a way, I feel you don't actually need to understand them. So, so if you go, so this is actually, I mean, okay, I would kind of say that I understand them like a little bit, but actually the rules that I use are very simple. So if I have many data points, I use SGD, and I know I can't use kernels. And so actually, the way I make a decision is a very simple decision tree. It's actually very much like this. If I know the data is sparse, I'm not going to use a forest. And so, I mean, I don't need to know like how the Gini index is computed to know if a forest is going to work or not. So, I mean, so this obviously, you will do much better than what this chart can do or what an automated method can do, but it will get you like 90% of the way, I think. That's my opinion, at least.
Thank you. Any more questions?
Yeah. In front, maybe?
You could also try to learn this chart. If you just have a lot of different machine learning tasks, then, you could also try to learn this chart if you have a lot of different machine learning tasks and a lot of different data sets. That will also make sense. And maybe at Amazon, you have access to that many different resources and approaches. So.
Yeah, but then I can't publish it. Yeah, actually, I mean, there's, so this one here, Hyperopt in the middle, is done by James Bergstraw, and he kind of worked on things like that, where you like learn about sets of problems and when to use which method. More in an optimization sense he did that, but it's definitely possible, and it's something we should do more.
Yeah, I have a question regarding the approach to the automatic hyperparameter optimization. So you presented Bayesian optimization as the basic method for doing that, but you didn't talk a lot about the metrics or the objective function to be used. So I guess you could just simply use cross-validated accuracy or so, but then there would be the risk of like overfitting your data, your validation data. So what would the approach would be you would apply to that?
Okay, so you're asking whether I'm overfitting my like validation data.
Yeah, like if you apply like tons of different algorithms with many different many parameters to be fit, hyperparameters, and like you have a huge search problem, and there would be like a huge potential to overfit your validation data then.
Yeah, I mean, you can regularize your optimization method, and obviously you should in the end have an additional test set to validate what you found. And there's probably, I mean, there's no other way out than if you want to optimize over a lot of parameters, then you need to have the data. But on the other hand, if I do this now, I'll also overfit. So it doesn't really matter if I do it manually or automatically. Maybe automatically I can try a couple of more models, but even manually I would try a lot of models. And so probably we all do this overfitting right now. But I mean, there's no canned answer for that.
This is not really a question, it's more like a comment. So we've seen that, okay, machine learning, sometimes you can change the methods, but you get more or less the same results as in logistical regression, linear kernel machine. It gives more or less the same results for some problems. So the key is actually all the features that you're creating. So if you're actually going to make like this easily to use, just click a button to test everything, maybe you also need to give like results, like ideas, what's working and what's not working. Like, because when I get a result, I don't compare with the second one. I say, oh, this is 0.1% better, so it's a better machine learning, or array, I made an improvement. I need to understand what the algorithm is returning. I mean, what feature did they use? I mean, usually I just go check the coefficients and see for specific examples what actually is finding. So this way of looking into the machine, I mean, into the actual model classifier is maybe more important. Probably like giving a simple return, like, I mean, okay, this is your model, this is your results, and this is what I think it's doing somehow. I mean, this is what it's working.
So I totally agree. I mean, it's the idea is that after my machine spits something out, I have to, so to get a good result, I have to go in. And so I just want to sort of, let's say I designed a new feature, and so I want to test if this is good. I don't want to go through all the week of trying out all models, if the feature improves on any of the models. So actually, I would just want to click on my black box again and say, is this feature good? Is there a model where this feature will be important? And so definitely I want it to be automatic, but I also want to be able to open up the box and see what's happening.
Okay, any more questions? Okay, so if there's no more, there's one more question.
It's basically the same theme we touched upon earlier, but aren't you afraid that you just handle users who are not, well, aware how machine learning works, what the dangers of overfitting are, what the dangers of choosing the wrong model are, to just hand them a bigger gun to shoot themselves in the foot? So I'm thinking about the Excel crowd to basically get asked by their boss, they need to deliver a model by the end of day, the end of business. And then, well, just hectically import something from Excel, let's start an automatic model on it, get some promising looking results and deploy this. So I think that this impression is something becomes a commodity. It's easy to understand and easy to do. And I think it will be easy to do, but not necessarily easy to understand.
Yes, it will. But I don't think it's necessary for everybody to easily understand. So you say, yeah, I'm giving people a bigger gun to shoot themselves in the foot, but I would disagree because currently they might just pick any model at random and put any very dirty data in that, and so then they will get some sort of result. And maybe they don't do correct cross-validation, and maybe they overfit completely with their parameters because they don't do any cross-validation at all, or they just train on their whole test set. But if this process is more automated, actually the people who know more about the models can help build a process that prevents them from shooting themselves in the foot. So I can build it in a way that it will always do cross-validation.
Okay.
Okay, so let's thank Andy once again.